So, today I am going to discuss about that whatever we have done in the previous lecture. We have shown that the dimension of u plus w is equal to dimension of u plus dimension of v minus dimension of u intersection w, not v, it is w, where u and w are the subspaces of a vector space V, and V is a finite dimensional. So, suppose I take the dimension or maybe I can say that V is a finite dimensional vector space. Now, from here I can say that if u intersection w is 0, just it contains the 0 element. From here we can say, then I can write that the dimension of u direct sum, it will become the direct sum, then it will be equal to the dimension of u plus dimension of w. So, for the direct sum we directly can write as dimension of u plus w is equal to dimension of u plus dimension of w. So, these things we can write down. For example, suppose I take the vector space V, I take R3. So, dimension of V is 3. So, let we take the subspace U. So, I just take the subspace and I take the subspace U as x, y, 0. So, all the element, so I can say that this is a xy plane. I can take the another subspace W, that is 0, y, z. So, I can say that the elements coming from y and z space. So, this is, I just write y z belongs to real line and it is basically y z plane. In fact, I can also write here that x and y belongs to real line and that is equal to xy plane, and this is, maybe I can write y z plane. Now, from here you can see that in this case, if I take u intersection w, so it will contain all the elements which has element coming from u. So, u is, if it is u coming from u, then it will contain the third coordinate 0, and if it is coming to w, the first coordinate 0. So, it means if you take the u intersection w, that will contain only all the elements that which has 0, y, 0, where y belongs to real line. So, basically it is equal to a y axis. So, it contains all the elements lying on the y axis, and we also know that the dimension of u is 2, dimension of w is also 2, and dimension of u intersection w is just the one line. So, it is 1. So, that is a just y axis. So, from here you can see that the dimension of u is 2, 2 and 1. So, now from here I can write directly that the dimension of u plus w will be 2 plus 2 minus 1. So, that will be 3, and from here it says that since the dimension of u plus w is equal to the dimension of v, which implies that u plus w is itself r cube, and that is also true in this case, because I am taking all the elements from xy plane and from yz plane. So, u plus w will contain all the bases of it, because it is spanned by, we know that u plus w is spanned by basis of, or maybe I can write down of u and w. So, if I take the set S that is spanning set for u and spanning set of w. So, I just take the span of this one. So, it becomes u plus w, that we already know. So, from here I say that u plus w becomes in fact the whole vector space V. Now, if we take W, or maybe if we take another subspace S that is contain only z axis, then if I take u plus, so u intersection S, so then you, from here you can see that u is just xy plane and S is a z axis, so it will contain only 0 element, and from here I can say that the dimension of u intersection S will be 0, because it will contain only one element, that is a 0 element. So, from here I can say that the dimension of u plus S is equal to 2 plus 1, that is equal to 3, because the dimension of S is just 1. So, from here I can write that this will be a direct sum. So, this one we can find out the dimension of a direct sum, or it is not the direct sum, then we can use this theorem. So, after this one we define the another terminology, and that is called coordinates of a vector. So, let us define this one. Let I take a set B, it is V1, V2 up to Vn, be an ordered set from vector space V. So, it is ordered set, means we cannot change the order. If it is a V1, then it will be V1, V2, whatever the order is there, the element or the vector will lying in the same order. So, if it is a ordered set from the vector space V, then a vector V from capital V can be written as, so now take V, so it is ordered set from the vector space V, then a vector V, so it is not the ordered set, I can say it is the ordered basis from vector space V, then any vector V from can be written as some alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. So, now I have written the linear combination. Then then the vector that is alpha 1, alpha 2, alpha n is called the coordinates is called the coordinate of a vector v belongs to V with respect to basis B. So, from here I can write that I can write like this one. So, this one alpha 1, alpha 2, alpha n, it can be written as these coordinates of V related to the basis B. So, this is represented like this one. Now, so this is the way we can define. Now, if the coordinates of a vector are related to standard basis, then it is called coordinates of a vector, because here it is coordinates of the vector V with respect to the basis B. But if we take the coordinates of the vector related to the standard basis, then they are just called the coordinates of the vector. For example, suppose I take the vector 2, 3, 4, minus 1, and that belongs to R4. Now, we know that the standard basis for R4, so this is just 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So, these are called the standard basis, and we represent by E1, E2, E3 and E4. So, these are called the standard basis. Now, from here I can write that 2, 3, 4 minus 1, it can be written directly as 2 E1 plus 3 E2 plus 4 E3 minus 1 E4. And so, I am writing a vector V as a linear combination of the basis, standard basis of R4. So, from here you can check that my alpha 1 is 2, alpha 2 is 3, alpha 3 is 4 and alpha 4 is minus 1, and which is same as the coordinates of this vector 2, 3, 4, minus 1. So, from here I can say that the set 2, 3, 4, minus 1. So, this is the coordinates of the vector 2, 3, 4, minus 1. So, this one I can write here because this vector belongs to R4. So, this is the vector and its coordinates are this one. Okay, so, from here I can say, or maybe I can say that, so is the coordinate of the vector this. So, I am writing like this one, it means I am talking about the standard basis. So, it is a coordinate means the whole vector we are taking. We are talking about the whole vector, this one, and the element of these are the coordinates. Now, from here let us take the another example. The question is that find coordinates of 2, 3, 4, minus 1 relative to the ordered basis. So, here I am taking the basis. So, basis is 1 1 0 0 and then 0 1 1 0 0 0 1 1 and 1 0 0 0. So, these are the bases I am taking, and we are talking about. So, this vector V is basically 2 3 4 minus 1, it is same. So, it belongs to R4, that we already know. So, it is a basis of this one. So, it means that these vectors are linearly independent and it spans the whole R4. So, that is the basis. Now, I need to find out the coordinates of this one related to the ordered basis. Now, so for this one we need to write, so to find the coordinates we need to write the vector 2 3 4 minus 1 as a linear combination. So, suppose I take here alpha 1 1 0 0 plus beta 0 1 1 0 gamma and delta, where this alpha, beta, gamma, delta, they are belongs to the scalar field. So, these are the coming from the field basically. These are the scalar and coming from the field. So, I am taking this as a real numbers here. Now, we need to find this alpha, beta, gamma, delta. So, because these are the coordinates of this vector related to the basis B. So, from here if you see, it is a just linear combination. So, if I put a matrix and this vector as a column 0 1 1 0 0 0 1 1 and 1 0 0 0, and if I put here as alpha, beta, gamma, delta, this should be equal to 2 3 4 minus 1. So, it is a 4 cross 4 system. Now, in fact, here we cannot change the order. So, order means this is my first, second, third, fourth, because if I change the order, then this value of alpha, beta, gamma will also change. So, we cannot change the order, because we know that if we swap some columns of the given matrix, then the result will be changed. So, now from here I will get this. So, this one we need to solve. So, it is a 4 by 4 system. So, you can check that this is equal to Ax is equal to B, and we need to find the solution for this one. So, the best thing for this one is to reduce this into the echelon form and then find the solution. So, for this one I will write the augmented matrix . So, the augmented matrix I can write directly. So, this will my augmented matrix. So, I can write from here. So, it will be 1 1 0 0 0 0 0 1 1 1 0, and this one I will write as 2, 3, 4, minus 1. Now from here I will write minus R1 plus R2, because I need to make this element 0. So it will be 1, 2. So minus 1 plus 1, it will be 0. So it will be 1, 0, and minus 1, so it will be minus 1, and minus 2 plus 3, it will be 1, and all other element will be same. 0, 1, 0, minus 1. So from here I get this matrix. Now I need, so this is my pivot element, this is also pivot, so I need to make this element 0. So from here I will write minus R2 plus R3. So it will be 1, 2, and then 0, 1, 0, minus 1, 1, 0. So I am minus 2, minus R2 plus R3. So this will be 0. So this will be 1, and minus minus 1. So it will be 1, and minus 1 plus 4. So it will be 3, and then this will be minus 1. So I get this value. Now from here you just check, it is my pivot, this is a pivot, this is a pivot. So the last I can apply minus R3 over R4, and ultimately I will get 1, 0, 1, 0, minus 1, 1, 0, 0, 1, 1, 3. So it will be minus 1 plus 1, 0, minus 1, and here it will be minus 1, and minus 3 plus minus 1, minus 4. Now it is an echelon form, and because it is a 4 cross 4 matrix, so now from here, so this is my equal to U, the row echelon form. So from here I can directly, I can write that so I can write from here minus delta is equal to minus 4. So that gives you delta is equal to 4 from the last equation, because we have to do the back substitution, and from here I can write gamma plus delta is equal to 3. So that gives you gamma is equal to 3 minus delta. So 3 minus 4, that is minus 1. So gamma is coming minus 1. Now from the second last equation, or the second equation, it will be beta minus delta is equal to 1. So that gives you beta is equal to 1 plus delta. So it is 1 plus delta is 4, so that is equal to 5. And from the first equation, it is alpha minus delta is equal to 2. So that gives me alpha is equal to 2 plus delta. So it is 2 plus 4, that is equal to 6. So it is delta is coming 4, gamma is coming minus 1, beta is coming 5, and delta is, it is plus, I think, is equal to 2. So now from here I can add alpha is equal to 2 minus delta. So it is 2 minus 4, it is minus 2. So now from here all this we can, from here I can write that my coordinates, so this is the coordinates, minus 2, 5, minus 1, 4. So, now we can write that this is the coordinates of vector. So, the vector we have started with, it is 2, 3, 4, 2, 3, 4 minus 1 with respect to the basis B. So, this one I can write. So, these are the coordinates of this vector with respect to the basis B. So, that is minus 2, 5, minus 1, 4. So, this is the way we can find out the coordinates of any vector related to the given basis. So, that is one of the way we can define the basis. Now, so based on this one, I want to discuss one more important, that how we can use the extension theorem to extend the basis. So, for this one I just want to do one important example. So, let suppose we have vector space P3x. So, that is set of all polynomials of degree less than or equal to 3, and suppose x belongs to some interval I. So, I take the vector space V as P3x, and also I know that the dimension of V will be 4, because it is a polynomial of degree less than or equal to 3. So, its dimension is 4, we know that. Now, let we have two subspaces of V. So, I take the first subspace U as I just take the subspaces U, and I am taking all the polynomial P belongs to V such that P of 1 becomes 0. Means I am taking all the polynomial from this vector space V such that 1 is the root of that polynomial, and I take the another subspace W, that is P, all the polynomials from V such that P dash 1 is 0. Now, the question is, check U plus W, U intersection W, U W in terms of dimension, basis, and the extension of each of these bases. So, each of these bases means the basis of U plus W, U intersection W, U and W, basis to the basis of V, the basis of V. It means so to the basis of V. So, means first I need to find out what are the bases of U plus W and U intersection W, U and W, and then we have to write its dimension, and then we should be able to extend these bases to the basis of V. So, that is the question. So, we know that dimension of V is 4, because it is V is basically all the polynomial of type a plus bx plus cx square plus dx cube, such that a, b, c, d are real. So, it is space of all these polynomials, and we also know that the standard basis for V is 1 x, x square and x cube. So, this is the standard basis for the set of polynomial of degree less than equal to 3, and it is a 4 number. So, we know that its dimension will be 4. So, we will continue. So, let me stop here. So, in this question we need to find out that how we can find out the dimension, the basis for different subspaces, and we will continue this example in the next lecture. So, thanks for watching. Thanks very much.